In this video, we're going to take another look at a titration example. We are told we need to infuse Ozimek, not sure if I'm saying that right, doesn't really matter, 2 milligrams in 250 mLs D5W. The titration rate is between 1 and 3 micrograms per minute, and this is to maintain a heart rate greater than 50 beats per minute and less than 130 beats per minute. And we can see we have a blood pressure parameter as well, greater than 90 millimeters of mercury. So our patient, 55 years old, weighs 210 pounds, and we have the height. In this video, these are the pieces that I'm going to go over. We're going to take this information, and given this order, we're going to first determine what we need to administer via the IV pump. What rate do we need to calculate and then set for the IV pump to administer the minimum dose? Then we're going to use that dose and rate to calculate the factor number, also called the constant of variation. And we're going to model this situation with an equation. And then once we have that equation, we can use it to address additional questions, specifically one related to, once the patient stabilizes, what is the dose that the patient is receiving? So let's jump into the first part, determine the initial milliliter per hour flow rate. Just like we saw with the critical care examples, what we need to do is to administer the initial dose. Now, sometimes we are told specifically, we're given a range of doses, minimum to maximum, and we're also given an order where it says give this amount. But since we're not given a clear indication of give this amount, we're going to start with the minimum amount. So what is the initial milliliter per hour flow rate? We're going to take that minimum dose of 1 microgram per minute, and we're going to, when we're done with our dimensional analysis, need to convert that into an equivalent form of milliliters per hour because we are setting an IV pump. Now this problem is slightly different than ones that we've seen because this is not a weight-based dose. This is not a microgram per kilogram per minute. This is just micrograms per minute. So we actually don't need to multiply by the patient's weight. We just need to go ahead and when we are converting our units, convert micrograms into milliliters and minutes into hours. Now minutes into hours should not be a problem. So if I'm just making a plan real quick, minutes to hours, I know that conversion. Micrograms into milliliters, if I'm thinking about my dimensional analysis. If I look at what's available to me, I see that there are 2 milligrams contained in 250 mLs of D5W. So that's telling me I need to convert micrograms into milligrams. And then once I have that, I can use that dosage strength there to convert the milligrams into milliliters. So I'm going to go ahead and do my dimensional analysis. 1 microgram over 1 minute. I want to convert first, let's do the micrograms into the milligrams so that we can get to the milliliters. This is very common with titration and critical care examples. We need to convert the micrograms into micrograms into milligrams using this conversion factor. Since we're canceling out micrograms, micrograms needs to be in the denominator of the conversion factor, and the relationship between milligrams to micrograms, 1 milligram is equivalent to 1,000 micrograms. Just by multiplying by that factor, if I were to stop right now, I would have the ratio of milligrams per minute. I would know the milligrams per minute. But we don't want that. We want to continue and cancel out milligrams to go into milliliters. I know that there are 2 milligrams contained in 250 mLs, and if I multiply by the ratio of 250 over 2, that will convert the number of milligrams into milliliters, which is the numerator of what I'm looking for. The final conversion factor we need is to multiply over a ratio of minutes to hours so that we can change or convert minutes into an equivalent number of hours. So now I am all set up. If I were to multiply by all these conversion factors, I would have what I'm looking for. So I'm going to take 250 times 60. I get 15,000. And in the denominator, 1,000 times 2, I get 2,000. So if you take 15,000 and divide it by 2,000, we're going to get exactly 7.5. And there's no rounding needed here because that's the exact value and that's the rounded value. And when I say that's the rounded value, we're going to set the pump for this exact value of 7.5. The pump is going to be precise to the nearest tenth of a milliliter, so there's no rounding needed here. And that's good because we got an exact value. We want to use the dose equal to 1 microgram per minute and the rate equal to 7.5 milliliters per hour. We want to use those two items to create a formula or create a equation that models this situation. So the first thing we need to do is to calculate the factor number, which we also know is referred to as the constant of variation, knowing that the dose and the rate vary directly. That's telling us that there's going to be this ratio that is invariant across all relationships here between the dose and the rate. So one way that we can find this is to use the formula the dose is equal to K times R, or the rate, where D is equal to the dose, R is equal to the rate. If the dose and the rate are directly related to one another, this is the relationship between them. This is just a reworking of the ratio D over R equals K. We know there's going to be that ratio of the dose divided by the rate is going to always equal this constant value. And if we rearrange that, that'll give us this equation of the dose will equal to K times R. And we want to be really clear what these values are. So I'm going to write them and introduce variables very much like we did in the previous week, where D is equal to the dose in micrograms per minute, and R is equal to the rate in milliliters per hour. This is going to be a really important step. A lot of students forget this step, and they find that when they plug values in, they don't remember what the units are. So always be consistent here. What is D? If you're using a variable to represent some amount, what specifically are you suggesting that is? And here it's the dose being in micrograms per minute and the rate in milliliters per hour. So what we want to do is to find this constant. We want to find this value that links the dose and the rate. And what we need in order to find that value is to plug in one instance of the dose and the rate that are related to one another. So we saw that when the dose was equal to 1 microgram per minute, the rate was equal to 7.5 milliliters per hour. That's what we saw. So now we're going to plug those values in. The dose, let's cancel that out. The dose was 1. The rate was 7.5. And we know that this ratio between them is going to hold. So what we need to do is to solve for that constant, solve for that factor number. So if I divide both sides by 7.5, I will get exactly 0.13 repeating. And if we round that to approximately, K will equal 0.13. We're always going to round the factor number or the constant of variation. We want to round this to the hundredths place. So we found that constant value. What that tells us is that the dose in this example can be found by taking 0.13 times the rate. This is the equation that we can now use to address more problems or more questions related to this situation. And that's exactly what we're going to do down below. We notice that the patient has stabilized, and it's stabilized, the pump reads 10 milliliters per hour. So if the pump is reading 10 milliliters per hour, we want to determine what's the dose. What is the patient actually receiving if the pump reads 10? So let's bring down this formula. We know the relationship between the dose and the rate can be represented with this formula, this equation. The dose is equal to a product of 0.13 times R. What are we given in this problem? We're given that the rate is 10.3. Or excuse me, the rate is 10 milliliters per hour, not 10.3. The rate is 10 milliliters per hour. What we don't know, or what we're looking to find, is the dose. So let's plug in 10. Let's plug 10 in for R. So the dose will be equal to 0.13 times the rate, which is 10. And if we multiply those, we get the dose is equal to 1.3. Now that's great. We found the variable d is equal to 1.3, but that doesn't really address this question. We want to make sure that we attach the unit or attach the label to this. So what does that mean? A lot of students forget at this point. They might put milliliters per hour, but let's look back. What did we say D is? D is the dose in micrograms per minute. So that's telling me 1.3 is a measure of micrograms per minute. So looking back over this entire problem, we needed to convert the initial dose into an initial rate. And that was telling us something about a relationship between the dose and the rate. And we used that, knowing that the relationship between those, there's a direct variation, we use that to find the factor number. We use that to find that constant of variation. And once we had that, and we had this equation, we can use this equation to address different problems. So in this particular problem down below, we were given the rate, and we needed to plug that in for R and solve for D. There may be times where you are given another dose, so you need to plug the dose in for D and solve for R. So you really need to be careful with these problems, and you want to read very carefully and make sure you understand what values or what variables you're using and what values you're plugging in for those variables.